Hi and welcome back. This is our 11th example about transient response of first order circuit. What we have is a RL circuit with two inductors in this case. So this is our first example with two inductors. We have a switch again, and we have an independent source, and we have three resistors R1, R2, and R3. The values are given here on the right side. What we like to know, as in the previous examples, we'd like to know the current through the inductor, but in this case we would like to know the current through L1 and also current through L2 as a function of time for time larger than 0. So the procedure is exactly the same, but we do it for two reactive components or two inductors. So let's start with the situation. Again, we will look at the situation before the switch closes, so for t less than 0. So what we have is, if I redraw the circuit again for this condition, we have the independent current source IP, which is connected in parallel with R3, and that will be connected to R1. And what we always do is we consider the inductors in this case and also in the next case for the calculation of the other parameters as a short circuit for calculation of the initial value and also for the steady state value. So I will use a short circuit for the L1 and also for the L2. So that's actually the situation here, and this is the current IL2 for the initial value, and we have also the IL1 for initial value. Alright, let me denote this node as X to make this clear for further calculations. What we can do here is actually use the current divider rule, but we have to be very careful, or you can use source transformation for this to go from the Norton equivalent circuit to the Thevenin equivalent circuit. I will use the current divider rule, which is easier and faster. How to do that, and where do you need to be careful when you carry out the calculation for that? If you want to know the current IL1, what you need is actually two resistors, so R1 and another resistor, but we have three resistors, so in total. So what we need is we need the equivalent of the R3 and the R2. That's actually what you need to write down, and it's actually the same story for the IL2. So if you want to calculate the current through this branch, you need again only two resistors, so R2 and another resistor. So this is actually the resistor which you need to make up as the equivalent resistance. So I will write it down as the expression. So IL is equal to the equivalent circuit R3 and R2. That's actually the other resistance, divided by the total resistance R3 in parallel with R2 plus R1 times the independent current source IP. And for the IL2, the initial value is the same story, but using R3 in parallel with R1 divided by R3 in parallel with R1 plus R2 times IP. Alright, so actually these are the formulas. So what we need is we need to calculate the R3 in parallel with R2, and that is R3 times R2 divided by R3 plus R2. So what we have is 40 times 10 divided by 40 plus 10. It will be equivalent to 8 ohms. And for the other one, R3 in parallel with R1 is R3 times R1 divided by R3 plus R1. And it will be 40 times 20 divided by 40 plus 20. So there will be in exact form 40 divided by 3, and approximately this is 13.33 ohms. So these are the two values we require to calculate the initial values of the inductor current. So I will do that. So I will use, for the first part, I will use 8 divided by 8 plus the R1, that's 20, times 0.5. That will bring us to the value of 1/7 amps. I will use this in the exact form. And the next one is 40 divided by 3. I will do it in parentheses. And then 40 divided by 3 plus 10 times 0.5, and it will bring us to 2 divided by 7. So 1/7 and 2/7. We have the currents for the initial value. So these are the initial values for the inductor L1 and inductor L2. Okay, the next step is calculating the situation for the final values. So how do we do that? So we will switch, the switch will be closed, and there is an interesting situation now. This branch is completely shorted off, so that means this is completely out of the picture. So what we have is actually this short and these two branches. So what you have is actually, after the switch is closed, that's very interesting, the stored magnetic energy in the inductors L1 and L2 will flow through the resistors R1 and R2. So they will lose their energy and they will dissipate their energy in the resistance R1 and R2. So that will also be the final value of the currents through the inductors will therefore be 0, because they will lose all of their energy. There is no other way to sustain the energy. So that's actually very interesting to note here. So because there is no other independent source left, the energy stored from the first condition will be dissipated completely in this second condition. So I will draw this situation. So what we have is for t larger than 0, what we have is actually the situation when the switch is closed. I will just emphasize it with a short, and we have still our resistance and the short for the L1 and the R1, R2, and the short for the L2, but the stored energy in these inductors will flow through the R1 and R2 as described just a minute ago. So what we need is actually to determine the time constants after we know the final values. So final values for both inductors will be 0. So IL final is 0 and IL2 final is also 0. That's very important. So again, the inductors will lose their energy, lose their magnetic energy after the switch is closed, because there is no other independent source which will sustain the energy in the inductors. So that's actually a very important situation. So what we have now is determining the time constants. How do we do that? Time constant. That's the next step. Time constant. Time constant. Okay. Now we can use the superposition principle here. Why? Because we have a linear circuit. So the circuit is linear, and we can consider each part as a linear component. And we can consider this as a current source and this also as a current source. So we can consider this part first and then ignoring this part. That means you can disable it. That means it will be open, and then we can determine what kind of resistance is seen by the inductor L1. Once you calculate that, you have this also the tau for the L1. You can move on to the L2 and then disable other components, that will mean this current source will be open because it's disabled, and this will see its own resistance, so it will also have its own time constant. So what you see is pretty straightforward. If you look only and consider only the L1, so make this active, this will be open, and the L1s will see only R1. And the same story is actually for the L2s, that will see only R2 because this is disabled. So what you have here, using the superposition principle, we can say the tau L1, so for the inductor L1 is actually this, and for the other tau L2 is L2 divided by R2. Okay, so we can fill in the values they are given. So what is the L1 and L2? L1 is 6 millihenry, so 0.006 divided by R1, and R1 was 20. That will bring us to the time constant of 0.3 milliseconds. So that's for the first inductor. The second inductor will be 0. So that will be 8 millihenry, 0.008 divided by 10, and that will bring us to 0.00 or 0.8 milliseconds. So that's actually these are the time constants. So this is actually the time constants for both inductors. And we are actually almost done because we have all the ingredients for setting up the formulas for the L1 and the L2. So let's do that. The current IL1 will be the final value. So I will write it down also. The final value plus the initial value minus the final value times e to the power minus t divided by tau L1. So let's fill in and simplify such that this can be read easily. Now, you know that this is 0. This is also 0. So this is actually the only part of it which is left. And this was 1/7 amps. So I will write it down just like that. And I have also here the tau L1, and tau L1 is 0.2 milliseconds. So what we have is 1/7 times e to the power minus t divided by 0.3 times 10 to minus 3. And if you make this also readable, then you get 10 to the power 4 divided by 3t. So 1/7 times e to the power minus 10,000 divided by 3t, and it is in amps. In the same manner, so we can use the EL2 is EL2 for the final condition, and in parentheses the EL2 in the initial minus the final, and then e to the power minus t divided by TL2. So let's fill in what we have. Again, the final values of the final values are 0, and the initial value had 2/7. So that's actually the last part, 2/7. So what we have is 2/7 e to the power minus t divided by 0.8 times 10 to minus 3. So I will also simplify this. So what we get is 2/7 times e to the power minus 1250 t, and that's also in amperes. So that's actually the two expressions for the currents through the L1 and L2. The complete expressions are like this, and if you want to see this graphically, let's do that also. Let's make a sketch how this will be. So this is the y-axis, which is the current, and this is the time. So I will do this IL, and it is also in amps, and IL2, and also in amperes. I will do the IL1 in red, and I will do IL2 in blue. So what we have, what you see is at time equals 0, it will start at 1/7 and it will die out to 0. So actually, let me also make this clear. This is 0, this is 0. So I will start at 1/7 and I will die out very fast to 0. And for the blue one, I will start at twice as high, and I will also go to 0, but this will be also going to 0. So it will be, of course, not a linear function. Okay, so this blue is the IL2, and the red one, this one, this will be IL1. This will give us the sketch for the currents through the inductors. Alright, this was an example which is actually a different example of compared to the previous example. You have two currents compared to the other examples. It will also give you more insight about what happens through each branch if you want to add up or use this in further processing. Now, thank you very much. I hope this is helpful for you, and I will see you next time. And don't forget to share and like. Thank you very much.